Today we're going to explore one of the most fascinating phenomena in soft matter physics, the capillary origami effect. This is where a flexible membrane spontaneously folds into precise three-dimensional shapes when placed on a liquid droplet, driven purely by surface tension. Capillary origami is a phenomenon where interfacial tension forces cause thin elastic membranes to fold and deform into complex three-dimensional structures. No external force is applied, yet the geometry emerges spontaneously from the competition between elasticity and capillarity. Picture this. You have a liquid droplet sitting on a surface, and you gently place a thin, flexible membrane on top of it. The membrane could be made of plastic, rubber, or even a thin metal foil. As soon as the membrane contacts the liquid, surface tension begins pulling at the contact line. What happens next is remarkable. The membrane doesn't just sit flat on the droplet. Instead, it spontaneously folds, creases, and wraps around the liquid, forming intricate three-dimensional shapes. No one is pushing or pulling on the membrane. The geometry emerges entirely from interfacial forces. Let me give you an analogy from everyday life. Have you ever noticed how a wet t-shirt clings to your body in specific patterns? This is a manifestation of the same principle. When water soaks into the fabric, surface tension at the water-air interface pulls the fabric into curves and folds that follow the contours of your body. The fabric doesn't want to be flat anymore because the surface tension creates a pulling force at every contact line between the wet and dry regions. Now you might ask, why do we call this a paradox? Here's the paradox. How can a liquid, which is formless and flows freely, create precise geometric structures? Liquids themselves have no inherent shape. They conform to whatever container they're in. Yet when coupled with a flexible membrane, the liquid-air interface acts like an invisible sculptor, folding the membrane into mathematically precise polyhedra, cylinders, and other geometric forms. The resolution of this paradox lies in energy minimization. The combined system of liquid, membrane, and surface interfaces seeks the configuration that minimizes the total free energy. This leads to predictable, reproducible shapes, even though no external force guides the folding. To understand capillary origami quantitatively, we need to look at the two competing energy scales in this problem. The first is the surface energy. This is simply gamma times A, where gamma is the surface tension coefficient and A is the total area of the liquid-air interface. For water and air, gamma is about 72 millinewtons per meter. The second is the elastic bending energy of the membrane. This is 1/2 B kappa squared times L, where B is the bending stiffness of the membrane, kappa is the curvature, and L is a characteristic length. The bending stiffness depends on the material's Young's modulus and thickness. The total energy is the sum of these two contributions. The system will spontaneously evolve toward the configuration that minimizes this total energy. This is a fundamental principle in physics. Systems at equilibrium sit at energy minima. Here's an important question. Under what conditions will the membrane actually fold? When will it remain flat? The answer depends on a dimensionless number called the elasto-capillary number, which compares the relative strength of elastic forces to capillary forces. The elasto-capillary number is defined as B divided by gamma times L squared. B is the bending stiffness, gamma is surface tension, and L is a characteristic length scale like the droplet radius. When the elasto-capillary number is small, much less than 1, capillary forces dominate. The membrane is relatively compliant compared to the surface tension forces, so it folds easily. This is the regime where capillary origami occurs. When the elasto-capillary number is large, much greater than 1, elastic forces dominate. The membrane is too stiff to be deformed significantly by surface tension. It remains relatively flat, and capillary origami does not occur. Let's work through a concrete numerical example to see when capillary origami is feasible. Consider a water droplet with radius r equal to 1 millimeter sitting on a surface. We place a thin plastic membrane on top with thickness T equal to 10 micrometers. The surface tension of water is 72 millinewtons per meter, which we write as 72 times 10 to the negative 3 newtons per meter. The bending stiffness B is given by Young's modulus E times thickness cubed divided by 12 times 1 minus Poisson's ratio squared. For typical plastics, E is around 1 gigapascal, and nu is about 0.3. Plugging in numbers. 1 gigapascal times 10 to the negative 5 meters cubed, divided by about 11, gives us approximately 10 to the negative 16 Newton meters. Now we calculate the elasto-capillary number. B is 10 to the negative 16, gamma is 72 times 10 to the negative 3, and L squared is 10 to the negative 6. This gives us approximately 0.001, which is much less than 1. Since the elasto-capillary number is much less than 1, capillary forces will dominate and the membrane will fold. This is the perfect regime for observing capillary origami. Another crucial equation governing this phenomenon is the Young-Laplace equation, which relates pressure differences across curved interfaces to surface tension. The pressure jump across an interface is gamma times the sum of 1 over R1 plus 1 over R2, where R1 and R2 are the principal radii of curvature. This equation tells us that curved interfaces create pressure differences. The pressure inside a curved droplet is higher than outside. This pressure difference acts on the membrane, providing the mechanical force that causes it to bend and fold. The curvature of the interface dictates the magnitude of this pressure difference. For a spherical droplet, both radii of curvature equal r, so the pressure difference is 2 gamma over r. This creates higher pressure inside the droplet, which pushes outward on any membrane covering it. One of the most striking features of capillary origami is that it can produce highly symmetric geometric shapes, including the platonic solids. If you place a triangular membrane on a droplet, it can fold into a tetrahedral shape. The 3 corners of the triangle meet at a point above the droplet, creating a perfect tetrahedron with the liquid trapped inside. Square membranes can fold into cubic or pyramidal structures depending on the volume of liquid and the size of the membrane. The edges of the square become the edges of the polyhedron. By patterning the wettability of the membrane or controlling the droplet volume, researchers can program specific three-dimensional shapes to emerge. This is a form of self-assembly where chemistry dictates geometry. You might wonder, what exactly determines which shape the membrane will fold into? Is it random or predictable? The final shape is determined by the boundary conditions, the initial symmetry of the membrane, and the volume of liquid. If the membrane is triangular, the threefold symmetry favors tetrahedral outcomes. If it's square, fourfold symmetry favors cubic or pyramidal forms. The contact angle between the liquid and the membrane also plays a crucial role. A highly wetting liquid will spread more on the membrane, leading to different folding patterns than a non-wetting liquid. The contact angle theta is determined by Young's equation, the arcosine of gamma SV minus gamma SL divided by gamma LV, where these are the solid vapor, solid liquid, and liquid vapor surface tensions respectively. So why do we care about capillary origami beyond its aesthetic beauty? This phenomenon has important applications in several cutting-edge fields. Capillary origami offers a way to create complex three-dimensional microstructures without expensive lithography or molding. You can pattern flat membranes and let surface tension do the folding automatically. Imagine electronic circuits printed on flat sheets that automatically fold into three-dimensional configurations when exposed to a liquid. Or solar panels that self-assemble into optimal geometries for space applications. In biomedical engineering, capillary origami could create microcapsules that hold drugs and release them in a controlled manner. The folding creates sealed compartments that protect the payload until triggered to open. The process is remarkably simple. Start with a flat pattern sheet, add a droplet of liquid at strategic locations, and watch as the sheet folds itself into the desired three-dimensional form driven purely by interfacial forces. Let's delve deeper into the energy landscape that governs capillary origami. Understanding stability is crucial for applications. The energy landscape often contains multiple local minima, meaning there can be several metastable configurations. The system might get trapped in one of these local minima rather than finding the global minimum energy state. The total energy is the surface tension times the total interface area plus the integral of 1/2 b kappa squared over the entire surface of the membrane, where kappa is the local curvature at each point. Even if a lower energy state exists, the system might not reach it if there are kinetic barriers. The membrane might get stuck in a local configuration because the energy required to unfold and refold exceeds what thermal fluctuations can provide. The folding dynamics depend on temperature and the viscosity of the liquid. Higher temperatures increase thermal energy available to overcome barriers. Lower viscosity liquids allow faster reconfiguration during folding. Cutting-edge research focuses on programming not just the final shape, but the entire folding sequence through clever design. By using droplets with different evaporation rates, researchers can create sequential folding where one part folds first, then another, creating complex assembly pathways that wouldn't occur with simultaneous folding. Chemically patterning the membrane surface with hydrophobic and hydrophilic regions controls where droplets sit and how they spread. This allows precise control over which parts of the membrane experience capillary forces. Here's a schematic showing a membrane with patterned wettability. Red regions are hydrophilic and attract water. Green regions are neutral, and blue regions are hydrophobic and repel water. This pattern determines where droplets preferentially sit. Let me give you another analogy to build intuition. Imagine trying to fold a piece of paper, but instead of using your hands, you place small magnets at specific locations on the paper. The magnetic attraction between magnets on different parts of the paper represents the capillary forces pulling the membrane at contact lines. As magnets attract each other, they pull the paper into folds. The stiffness of the paper represents the elastic resistance of the membrane. Thin paper folds easily, like a compliant membrane. Thick cardboard resists folding, like a stiff membrane. Just as the balance between magnetic force and paper stiffness determines whether the paper folds, the balance between capillary forces and membrane elasticity determines whether capillary origami occurs. One fascinating aspect of capillary origami is how it scales with size. The phenomenon becomes more dominant at smaller scales. The ratio of capillary forces to gravitational forces scales as gamma L divided by mgl, which simplifies to 1 over L squared. As length scale L decreases, this ratio increases, meaning capillary forces become more important at small scales. At millimeter and submillimeter scales, capillary forces completely dominate over gravity. This is why insects can walk on water, and why capillary origami works so well at these scales. At meter scales and larger, gravity dominates, and surface tension effects become negligible. You can't use capillary origami to fold large sheets of material because gravity overwhelms the interfacial forces. The characteristic capillary length is the square root of gamma divided by rho g, where rho is density and g is gravitational acceleration. For water, this is about 2.7 millimeters, defining the crossover scale. Here's an interesting question. Once the membrane has folded via capillary origami, can we reverse the process and unfold it back to its original flat state? Yes, the folding can often be reversed by removing the liquid. If the membrane hasn't undergone plastic deformation, evaporating or withdrawing the liquid will allow elastic forces to restore the membrane to its flat state. However, hysteresis in the contact angle and friction between surfaces can complicate the unfolding. The membrane might not return to exactly the same flat configuration, especially if adhesion between folded surfaces has occurred. To create permanent folded structures, researchers sometimes heat the membrane above its glass transition temperature while folded, then cool it down. This locks in the folded shape through plastic deformation. How do scientists actually observe and measure capillary origami in the laboratory? High-speed cameras allow researchers to watch the folding process in real time. The membrane typically folds within milliseconds to seconds, depending on the liquid viscosity and membrane stiffness. Optical interferometry techniques can measure the curvature of the membrane with nanometer precision. This allows quantitative comparison between theoretical predictions and experimental observations. Atomic force microscopy can probe the local mechanical properties of the membrane before and after folding, revealing any changes in stiffness or structure induced by the folding process. A typical experimental setup includes a camera positioned above to capture top-down views of the folding process with carefully controlled lighting to reveal the three-dimensional structure as it forms. Interestingly, capillary origami principles appear in biological systems, even though nature didn't explicitly design for this phenomenon. Pollen grains fold in characteristic ways when they dehydrate. The loss of water creates capillary stresses that cause the pollen wall to buckle and fold into specific patterns that are characteristic of each species. Some insects use capillary forces to help deploy their wings after emerging from the pupal stage. Fluid movement through wing veins creates pressure differences that help unfold and stiffen the wings. Even at the cellular level, membrane tension plays a crucial role in determining cell shape. While not exactly capillary origami, the same balance between tension and bending energy governs membrane morphology. From a mathematical perspective, capillary origami presents two challenging problems: the forward problem and the inverse problem. The forward problem asks, given a membrane geometry, material properties, and liquid volume, can we predict what shape will emerge? This requires solving coupled, partial differential equations for membrane mechanics and fluid interfaces. The governing equation involves the divergence of B times the biharmonic of the height field H equal to the pressure difference. This is a fourth-order partial differential equation that's challenging to solve analytically. Researchers typically use numerical methods like finite element analysis to solve these equations. The membrane is divided into small elements, and the energy minimization is performed computationally. The inverse problem is even more challenging and more useful for applications. The inverse problem asks, if I want a specific final shape, how should I design the initial membrane? Where should I place droplets? And what volume should they have? This is a design optimization problem. Solving the inverse problem enables rational design. Instead of trial and error, engineers could input a desired three-dimensional structure and receive a blueprint for the flat membrane pattern and droplet placement. Recent research has applied machine learning to this inverse problem. Neural networks trained on thousands of simulated folding events can learn to suggest designs that achieve target shapes with high accuracy. Despite its elegance, capillary origami faces several practical limitations that researchers are working to overcome. Current implementations are mostly limited to relatively simple polyhedral shapes. Creating highly complex geometries with many different curvatures remains challenging because of the difficulty in controlling multiple contact lines simultaneously. For volatile liquids, evaporation during folding changes the liquid volume and contact line positions. This introduces time-dependent effects that complicate both modeling and reproducibility. Finding materials with the right combination of flexibility, toughness, and surface properties is challenging. The membrane must be flexible enough to fold but strong enough not to tear. It must be compatible with the chosen liquid. When folded surfaces come into close contact, van der Waals forces and capillary adhesion can cause them to stick together permanently. This can prevent the structure from unfolding and may or may not be desired depending on the application. Let me conclude with some exciting future directions and open questions in this field. One major question is whether capillary origami can be extended to create truly complex organic shapes like those found in nature, rather than just polyhedral approximations. This would require much finer control over curvature. Integrating capillary origami with stimuli-responsive materials that change properties in response to light, temperature, or chemical signals could create dynamic structures that fold and unfold on demand. Researchers are exploring whether clever engineering could enable capillary origami principles to work at larger scales by using vacuum or pressure differences instead of surface tension, potentially for deployable space structures. Let's summarize the key concepts we've covered about capillary origami. The central principle is that precise three-dimensional geometry can emerge spontaneously from the competition between interfacial tension and elastic bending energy, with no external forces required. The dimensionless elasto-capillary number, comparing elastic to capillary forces, determines whether folding occurs. Small values favor folding, large values prevent it. Applications range from micro-scale manufacturing and self-assembling electronics to drug delivery systems and deployable structures, showing the broad impact of this phenomenon. The mathematical complexity of predicting shapes requires sophisticated computational tools, but progress in numerical methods and machine learning is making design increasingly tractable.